Hi, welcome to this lesson on calculus, sketching cubic functions. Let's have a look at question 4. So we're given the following information about the function g. G at 0 is 4. So when x is 0, y is 4. So this tells us the y-intercept of the graph. Then we have at -3, the y value is 0. So this tells us the potential x-intercept of the graph. Then g at -1 is 3. So we have a coordinate on the graph g given by -1, 3. Then we're given that g prime at -1 is 0. So that means at the same point -1, 3, because we have the coordinates, this is going to be a stationary point. So the tangent line at that point is going to have a gradient of 0. Then at that same point, -1, 3, can you see the second derivative is 0? So this potentially, so right there, potentially is a inflection point. Okay, that's only true if the derivative, the second derivative at that point is less than 0. So basically at an interval, so rather I should say this. So on the interval -infinity to -1, and on the interval -1 to infinity, we must either have a concave up, then concave down, or a concave down and then a concave up scenario going on. Okay, so it must change concavity if it is a inflection point. And then lastly, we're given g prime of x is greater than 0 for every real number x except at the point -1. So that means the function is increasing always. That's really important. So it's never decreasing. So it's always increasing, right? And then increasing again. Okay, so we want to sketch a rough diagram given this information. Okay, so let's go ahead and put the intercepts down first. So 0, 4, so that's up here somewhere. That's the y-intercept. And then -3, 0, that was the x-intercept. Okay. So we've used that two information. We have a point -1, 3, so we can plot that on our graph. So there's -1 and 3 is over here. So that's the point -1, 3. So let's go ahead and put that. And then it's also a stationary point, which means the graph turns there. Okay, or not necessarily turning, but just has a 0 gradient. And then it says at that same point, it could potentially be an inflection point. Okay, but we know that the graph is always increasing. So if I had to try to draw a rough sketch, I know that it must be increasing up to that point there, but then must still be increasing. So it goes up something like that. Now, can you see that the tangent lines lie above from all the x values up to -1? At -1, it's going to be a 0 gradient for that tangent line. So because the graph is down from the tangent lines, I would say that it's concave down from -infinity to -1. And then suddenly all the tangent lines are below. So the graph is up from the tangent lines. So I would say from -1 to +infinity, the graph is concave up. So at this point here, it is changing inflection from concave down to concave up. So this would be the most accurate representation of this graph given that following information. So we know it's a stationary point. More so, it's a point of inflection at that point. And it has increasing properties for all real numbers except at -1. So basically, the graph keeps increasing, inflects, so changes the concavity at that point, and also turns essentially. So if you zoom into this region here, if you like hone in and like have a magnifying glass, what's happening is that the graph's changing from concave down, turns here, and then goes back up concave upwards. Okay, so that is what's happening with this function, and that is how we would sketch it. Awesome. I'll see you in the next one.